Greetings. Okay, this is for Physics 204, summer of 2023. This is Wednesday, July 26th. The purpose of this video is to substitute for certain synchronized instructional class time today and to provide you with a brief walkthrough of the midterm exam that you are going to take, that will be posted tomorrow night, no later than 8 p.m., and that you will return to me by Sunday, 11:59 p.m., by midnight Sunday, July 30th. Now let me be more explicit. I'm about to briefly, but hopefully helpfully, walk through tips and techniques and partial solutions to the practice exam that you have in your possession that you just attempted during lab period, that you might be attempting more tonight. I'm going to walk through that document. I'm going to tell you again right now that your actual document, which will be posted tomorrow night, your document will be very similar to the practice document you have. The practice document that you have, of course, is the actual midterm exam from last semester, from the spring, and that's how it's labeled. And let me say again that anywhere here that I provide an exact answer or an exact solution step or something like that, that may well be a place where I will change numbers or change some details so that you don't just copy that into your actual exam and you show that you understand the concept. But any place, but I'm not promising full solutions to anything. Any place here where I just provide tips or a clarification, but I don't actually solve the problem, that's probably a signal to you that your problem will be possibly identical to the exact one that you see here. Let me say again also before I begin, that I feel that the first three problems in this exam are very directly related to either homework problems we've already gone over or to lab material you've already gone over. It's really the fourth problem that as yet I have said nothing explicit about. So my main purpose in this video, honestly, is to try and get to the very last problem and give you an overview of what I'm looking for in that very last fourth problem. A final thing also is please understand that there are a ton of videos. There's at least 3 videos in the playlist for last semester, 3 videos where I walk through their practice exam, which is very similar to this one. And so there's a lot, and I give full solutions to a lot of things there, and it's fair game. I highly encourage you to poke around the videos that have the term midterm in them from last semester. The main reason I'm doing this is just that that you have to poke around those and you have to skip around and find what you're looking for. So I'm just going to try to condense that to this today for here. But the most expansive help you could get would probably be from the videos from the playlist from last semester. They are fair game. Also, let me remind you one last time, anything is fair game for this exam. It is take home. It is open universe. You can consult sources even while you're doing it, but you have to understand that I understand that you're doing that. One of the reasons I give open universe exams, which I have been doing for a while, even sometimes before COVID, one of the reasons I do that is to level the playing field. To my mind, what cheating is taking advantage of a situation in a way that your peers cannot. What I believe cheating is when one individual takes it upon him or herself to do something that all other honorable individuals are restraining themselves from doing, and thereby give. So I think cheating is when somebody gives themselves an unfair advantage and takes advantage of the fact that other people are trying to play fair. So one of the reasons I give an open universe exam is so that we all have access to all of the same things, so that all of the things that you get it. So have at it. Help each other. Use the web. Use my old videos. Use whatever you want. But know that I know that you're doing that, so that at the end of the day, your job is not to provide correct answers. We already know that all of us have the correct answers. Your job is to show me that you have come to a point where you really have internalized why these answers make sense and are derivable from first principles, right? So just a reminder again, you can do anything you want to take this exam. I highly recommend that you do a rough draft first and then a final copy. Presentation absolutely matters in this case for the reasons I just stated. Okay, all right. So I'm going to start walking through. I'm going to flip back and forth between screens here. Again, this is and your exam will have the same kind of rules, the same expectations, all that. Let me just switch back and forth the documents. Okay, so. Hold on. Okay, you should see momentarily. Yes, all right, so this is the document that I'm talking about. Again, your document will be very similar to this one, right? So it has a cover page, okay. We will update the Pokemon this semester to be perhaps a grass type. So as you see, all these equations are given. This does not mean you have to use all of these equations. Some of these you won't use, but you can use any of them. They are regarded as first principles. Things can, for the most part, things can be derived from these equations. For the most part, these are like GDPs, general definitions and principles that you would use in step 3. You can also use things that you find on the web and stuff like that, but you got to be careful. If they're not a first principle, if they are a derived result, you have to derive the result and you have to show that you understand it. Okay, but yeah, you can use any equations. Then there's these instructions. I think your instructions will be similar. Maybe it says here, you have to choose one of the first 2 problems, and then you have to do number 3 and you have to do number 4. Just to be clear about that too, you can't get extra credit by doing an extra problem. There's many other ways to get extra credit in this class and maybe even after the exam is over, but don't look for it where it's not provided. What you certainly cannot do is do part of question 1 and part of question 2 and hope that I add the points together to make one complete. No, you have to choose and commit and fully solve whatever you fully solve, okay? And if you do everything, I'm just going to grade the first things I see. Okay, I think this is all clear. Yeah, the bottom line on page 3 is just another reminder. If you want to know what constitutes cheating or what doesn't constitute cheating in an exam of this nature, at all times, just ask yourself, if Yaverbaum called me into his office or called me in for a Zoom meeting and asked me to walk through this exam with him, kind of the way I'm about to with you, if I asked you to walk through and explain things to me vocally, like how you got it, would you be able to do it? How conversational could you be with me about it? If you couldn't defend what you were writing, then you don't understand it well enough to be writing it. Okay, I think you get it. Okay. All right. So this first problem again, maybe the words will be different. Maybe the physical objects will be different. But as you can see, as I hope you realize, this first problem is very, very similar to your homework 3. You are provided with a situation described by a differential equation. It specifically is the one and only differential equation that we've been studying in this class. Wait, can you see? Yeah, you can see. Okay. It is the one and only differential equation that so far we've been studying in this class. It is the differential equation that describes simple harmonic oscillation. Again, perhaps like I said yesterday in class, we've never seen an equation before with a capital C in it. And we've never seen an equation before with the number 98596 in it. But what we have, but C is a dependent variable here. And 98596 is a constant. What we have seen, what we've been studying is equations of this form, where the second time derivative of some dependent variable equals -1 times some constant times the dependent variable itself. That is the difference. So this thing that you're staring at very deliberately has the form of the differential equation for simple harmonic oscillation. I'm going to switch boards now and start writing things. Again, I definitely encourage that you tune into the video from yesterday, because we did this in detail with the homework number 3 yesterday, which technically is due today, but that's fine. I'm going to switch boards in a second, but before I do, so you notice you're given this differential equation. It happens to be the variable, the dependent variable, the measurable quantity here happens to be coulombs of charge designated C that are located in this thing called a capacitor. Now, this is all real stuff. And in fact, we'll get to it in this course, but part of the goal here is to not get bogged down in, you're not expected to care too much about the background details of a device known as a capacitor. What you're supposed to recognize is how the variables and the constants are functioning in this relationship. And so the constant of proportionality is 98,596. That's a given. What's also given here is that the initial value, the initial value of the charge at time equals 0, is plus 20 coulombs. Those are the two important given pieces of information. I'm going to switch boards now. Now, again, let me warn you, I'm not going to do the whole 5-step method here. I'm just here to give you an overview on like how to read this exam or what to look for and stuff like that. You are expected to do a 5-step method for everything and give great detail in your solutions on your exam. But I feel like in all the past videos, we've emphasized that enough of what I'm looking for. Here today, I'm just going to try to give highlights. So I'm going to switch boards now and just say the highlights of what I would write about this problem. Okay. Okay. So and again, and I should also again clarify, some of you would do this problem and some of you would choose not to. I believe it was a choice between problem 1 or 2, but obviously I'm going to say something about one. All right, so problem 1, the key again was, and what, for a second. Okay. Right, that was a given. Also a given was that CO equals 20 C, 20 units of charge. Okay, those were the givens, right? Now I should draw a diagram. The diagram should be a cosine function. We talked about that. But to cut straight to the chase, what it seems to me is, I would write some general terms now. I would write some general terms about differential equations with Z in them to make it clear what I know about differential equations in general. But to cut to the chase here, so again, please take what I'm writing here as quick answers or quick helpful hints. This is not a full solution, but it does seem to me that this must be the case. Right, the key. Right. The key point. Okay, 2 key points here. 1, the most important thing you need to know, and you need to explain a lot, and you need to think through, is that if this differential equation applies, then C is oscillating harmonically in time. The amount of charge in the capacitor is washing up and down like a cosine function in time. It's starting at a value of 20 coulombs, right? But it's going back and forth at an angular frequency, which necessarily is the square root of that constant given in the equation, right? Again, this is just like problem 3 yesterday. It's also like problem 1 on homework 2. I mean, it's just like homework 3 yesterday. And I'm going to tell you right now, again, I'm not going to do it now because I think we've done it a number of times, but you've got to, the thing I just wrote, like even before you start solving these specific questions, you got to show where I got this C equals 20 cosine 100 pi t thing from, or where I got this C equals C naught cosine omega t. You have to take 2 derivatives of that to show that it would get you back this differential equation. Okay, I can't emphasize that enough. I'm just concerned about time, so I'm not going to do it right now. But that's part of your job, is to, at least at the beginning of the exam, not over and over again, but at least once in a big way, somewhere in the exam, show where that solution came from and why we believe that it's right. Now, another thing I want to note, so I'm saying omega, the angular frequency, must be the square root of whatever that constant is. Now, you may or may not have noticed, of course, you're allowed to use calculators for all this stuff, and you should set them in radian mode. You must set your calculator in radian mode. Depending on how you use your calculator, you might or might not notice that the square root of that number was specifically designed so that the square root of it actually is very nicely divisible by pi. If you notice a thing like that, it's probably not an accident, and it's probably there to help you, because we're talking about radians, which are more easily measured in multiples of pi. So I did that. I noticed, the square root of that number is 3.14 times 10 to the second. 3.14. It's 100 pi. Now, let me say right now, if I notice a thing like that in a problem like this, it's not an accident. It's probably going to make my life easier, and it also probably signals that I'm doing something right. So all the better if it separates the wheat from the chaff, so to speak. If you notice a thing like that, if you don't notice that the square root of that number is 100 pi, that's okay too. That's okay. You'll probably, it's because you can express numbers however you want as long as it's right. You may get to a point in the problem later on where you start noticing some coincidences or something. Whenever you notice it, cool, then make use of it. This is another reason it's good to do a rough draft first and then a final copy, especially when you already know where the whole thing is going. Okay, but little things like this will happen in physics. And again, it just separates a person who has real command from someone who's barely hanging on. But it's okay it's a number. The square root of, it's 31,400, however you want to write it. Okay, but so I did that. So what's the point of all this? Just to get to the chase of this one, like here, I don't know why I'm still in the color blue, but so here, omega, I'm saying omega is approximately, and it's approximate, but 100 pi radians per second, right? And so, for example, for the first question, so now you notice these questions are very similar to the one asked in homework 3, but they're not exactly the same. You have to read them carefully. Don't just copy your answers from one thing to another. To answer the next couple questions, I'm not going to do it all out. I will tell you that if you look up on videos, probably they are done all out somewhere in old videos, but maybe not. But what's the key that you want to work this all through? You want to realize that definitely standard frequency hertz. Oh, sorry, I guess we usually write like this. Sorry. Standard frequency hertz is always angular frequency divided by 2 pi, right? And if you look at the units, that makes sense. And period is always the reciprocal of standard frequency measured in hertz. So you can get, so I'm going to leave it at, so you can see why writing your angular frequency as 100 pi, it makes it sort of easier to see right away, okay, then the standard frequency here is going to be 5. I mean, if the angular frequency is 100 pi radians per second, and you divide that by 2 pi, then you get, did I say 5? I think I mean 50. You get 50 hertz as an answer for number 1. And then you flip that to say, okay, if it's doing 50 hertz, 50 cycles per second approximately, then it's taking one, then it takes 1 over 50 seconds, like 0.02 seconds to do one full cycle. Again, I'm saying numbers like 50. If you get some number like 49.999 because you didn't use pi, totally fine. Don't get worked up over that. There's rounding involved in all of these answers. So, okay. So I guess I'll just say, like, yeah, I think 50 would be approximately, I mean, the frequency would be approximately 50 hertz. Okay, then I'll note right now for anybody who's still listening with me, question 2. So you got to read these things carefully. This is where we would change details from a practice exam to a real exam. Yeah, question 1, it's literally asking how frequently does the capacitor cycle through the full range of total charge magnitudes from its maximum through 0 to its minimum and all the way back to 0. Okay, so that's what that's asking. It's asking for standard frequency in number 1. Number 2, now it's asking something about time, but let's read the question closely. It says, how much time will elapse before the very first time the capacitor is entirely empty of charge? Okay, it doesn't ask how much time until the capacitor returns to its initial value of 20, right? It asks how much time until it's empty of charge, till the charge value is 0, till the graph hits the x-axis, right? So this is equivalent to asking how much time would it take a mass on a spring to get to equilibrium, right? To be as clear as I can be, if you read the question carefully, it's really asking how much time will it take to complete a quarter of a cycle. I'll just say that. Right? Now this is the kind of thing you have to look out for on the exam, these kind of details. I'm sure if I were a student, I might think of that as a trick question. All I can tell you is I don't mean it as a trick question. It may be a tricky question. I do mean it as a question that will force us not to just memorize answers that we got to previous things, but actually understand concepts. So yes, I'm trying to make sure that you understand once you know period, there's all kinds of information that you can get from period. Period is the amount of time for a full cycle. So as long as you know the amount of time for a full cycle, we could get a half cycle or a quarter cycle or an eighth of a cycle. And what we're trying to teach here is how, when it comes to oscillation, the better way to analyze oscillation is to think of it in terms of cycles and fractions of cycles. Nothing is constant in oscillation except for cycle properties. Do you follow what I'm saying? Like, we wouldn't ask, it's not as practical to ask what's going to happen in 3 seconds. It's much more practical to ask what's going to happen in a third of a cycle or something like that. So the question is designed to make sure you're actually thinking about the concepts and you understand them. It is designed to keep you on your toes and have you not just like copy things. But I will, so please, and because I just walked you through it, maybe it'll be slightly different on your exam. Maybe it'll say a half cycle or so. You have to be able to read the English. A lot of all of this is about translating back and forth between symbols in English. But last thing I'll say too, as far as trick questions are concerned, I can tell you this. Yes, I want you to be alert. I want you to take this stuff seriously. I want you to think in terms of concepts, not memorization. That's why we allow you to have everything in front of you. I don't care about memorizing things. That happens naturally once you understand things. But I'm also not trying to trick you. So it's important to know, once you've read any question carefully, once you've gotten the overview of the question the first time, understand 2 things. 1, if you can see 2 possible different ways to interpret a question, if you're looking at a question, you're like, wait, he might mean this, but he might mean that. If ever there's doubt in your mind, assume that I do mean the simpler, more straightforward interpretation. Physics is tricky enough. I am not saying that physics doesn't trick us. I'm not saying that these questions can't be tricky, but I'm saying you can assume that I'm not looking for ways to deceive you. So if there's two possible ways to interpret a situation, it's just like what physicists actually do with the world. We're always looking for the simplest possible way to navigate the world. Even the simplest possible way is usually complex enough. So if you have two different ways to interpret a question, I am saying, yes, read it very carefully. Make sure you're taking the details seriously. But don't think to yourself, well, I feel like I know where this is going. But physics is always obnoxious and tricky, and he's probably just trying to mess me up. So it's probably like not what I think. No, I'm not trying to mess you up. It's messy enough. So go with your gut on what a question means. And if there's a lot of words, like like I always have, often, like even in like in the first question, it says, how frequently does this capacitor cycle through the full range of total charge magnitudes? Okay, through the full range of total charge magnitudes. The truth is, that is the question right there. That is enough to make the question clear to many of us. But just in case you don't totally get what I'm saying, or just in case there's any confusion, I'm then adding a parenthesis that I'm saying, like, from the maximum to 0 to the min. All those extra words are to reassure you so that you can go in your mind like, wait, is that, oh, yeah, that's what I'm picturing. Okay, yeah. Oh, okay, so he does mean what I think I mean. Like if I use extra words to try to drum in the thing, if you already got it, you got it, and move on. Don't think that the extra words are some new hidden secret crazy detail that are meant to make it even harder. They're just meant to confirm the question means what I hope you think it means, okay? When in doubt, go with the simplest interpretation of a question. And as long as you show what your interpretation is and you go with that, you'll usually prevail. Okay. Okay. But this is, again, why it's good to take your time reading. Okay. So by question, okay, I should move on very soon, but question 3 of problem 1. Now, you're literally being asked to find charge at a particular moment in time. This brings us all the way back to question 9 of homework 1. This is originally why we've solved the differential equation in the first place. This is literally asking you, to plug straight in to the equation. I mean, to plug straight into this, but not 220. And you would plug in 0.1 for t. It's literally asking you to plug in chug. Just please know your calculator must be in radian mode for this to work. Okay. Then question 4. I'll tell you right now, if you're still listening, as a reward for listening. Wait, am I? Yeah, I'll summarize what's going on in question 4. Question 4 is trying to get you to see, or just trying to drum in the idea that this is simple harmonic oscillation. Again, you will have explained that up at top in some detail. This is simple harmonic oscillation. And what does harmonic mean? It means that the angular frequency, and therefore the frequency, and therefore the period, is not a function of the amplitude. It doesn't matter how big the amplitude is. This thing is still going to go back and forth at a certain constant given rate. And I assure you again, I mean, if you think about that, and the more you think about that, you'll realize that there is a there. Like you'll know you're getting what I'm saying if you start thinking about it enough and you start actually thinking you don't believe me, because it actually is weird and it is a surprise. If it just sounds obvious to you, I'm not sure you're hearing me. But what I'm saying is it doesn't matter how much charge starts off in that capacitor. It doesn't matter if we start with 20 or 40. The rate at which all the charge will dump out and then come back, that rate in time will be the same no matter how big the job is. Because I am, in effect, saying the bigger the job is, the faster the job will occur, because the more potential energy, the more kinetic energy there has to be. And it works out perfectly so that the amount of time, the amount of angular frequency, and therefore standard frequency, and therefore period, will be a constant regardless of amplitude. So I'm saying your answers to, I mean, if you're listening, 1, and again, I might phrase the question differently tomorrow. Don't just memorize this, but understand it. Your answers to 1 and 2 will be the same. If you're and the explanation is because this is harmonic oscillation. The frequency does not depend on the amplitude. But 3, your answer will differ. It will differ. You will have to replug in because we're not asking about time at this point. Now we're asking about charge amount, and the amount of charge at any given time, of course, does depend on how much charge there was initially. You'll have to replug in the equation you did in number 3, and you will get a different answer. So again, you see, I'm not giving you the answers necessarily here, but hopefully this is a guide to what I'm looking for. So that was question 4. Okay. 5, I'll say very quickly because I know I got to make tracks here. 5, and I also don't know why I'm staying in the color blue, but I think I care more than you do. In 5, we're trying to get across the idea that all systems that can be described by this differential equation are all harmonic oscillators. And all harmonic oscillators, no matter what they physically look like, or even if we can't really see them at all, they're all ultimately act like masses on well-behaved springs. Again, that's why the whole course starts with a mass on a spring. Everything is based on that. So we're trying to say, if you understand that, then you could visualize this big capacitor. Even if you're like, I don't know what a capacitor is, I don't even know what he means by charge. Just visualize it as a big spring with a mass on the end going back and forth and back and forth. But that mass on the end represents amount, or the position of the mass in your mind, in the analogy, represents amount of charge in this box called a capacitor. So what they're asking is, how literally can we take that analogy, or how far can you take it? Could we actually calculate the stiffness of this metaphorical spring? Like, this isn't literally a spring, but if we're saying it's acting springy, how springy is it? Yes, we can do that. The bottom line to this is that the omega of this system is likened unto the square root of stiffness over mass from our original problem 1, right? So you could solve for stiffness, effective stiffness, by setting it equal to, to this, right? And it's effective because there is no actual spring here, but there's something acting springy. So the effective stiffness of it would be this. Again, you have to write this all out, but you see, that's what I'm looking for there, and you explain it. Lastly, 6. Okay. Oh, yeah, okay. I'll tell you right now. So the answer to this one is false. Definitely that is not a solution to the differential equation. There's 1,000 reasons why the answer is false for this. And again, I can tell you right now, your question, will be slightly changed, because even this, it is false, because there is like a typo here. I didn't even remember to put in the cosine word or the sine word or anything like that in the function. So for the second derivative to return the original function, it would have to be some kind of non-algebraic function like a cosine or a sine. There just doesn't even have a sine or a cosine. So it's false. If I put a cosine in there, well, also another thing that a student noticed also I said X by accident instead of C. So I will admit there were kind of some accidents in there, but that doesn't invalidate the question. It just makes the answer definitively false. Now, hopefully I'll be a little bit more careful with your question on your exam. Maybe that X will be a C, and maybe there'll be a cosine before that bracket or something. If I had said that, if I'd said C equals 20 times cosine of 100 pi t plus blah, 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 that would be true, right? Even with the plus blah, 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 like we showed yesterday, it would be true. If the number before the whole brackets weren't a 20, if it were like a 30, or here implicitly the number 1, then it'd be false, right? Because it says it has to be, I'm saying 20, I mean 40. This thing has to be a solution to the differential equation and satisfy the condition that C naught is 40. So for it to be true, I guess what I'm trying to say here is, for it to be true, it would have to be something like this. Something. I mean, there's other versions, but something. Right? Now, yeah, something like that. Now, the thing that we're about to get into here, I hope you understand why the 40 would have to be true for the 40 would have to be a 40 for this to be true. There would have to be something like a cosine or a sine for this to be true. The 100 pi would have to be 100 pi for this to be true. If it were 50 pi, it wouldn't be true, right? But also that extra term pi over 2 could be added for reasons that we just learned at the end of yesterday. And it's that I really want to get into more here. I'm taking too much time as usual. I want to get into that pi over 2 business. But suffice to say, from our conclusion yesterday, you can throw in a term there, and even if you take 2 derivatives, the term won't throw off those derivatives, so it would still be true. Okay, so as it's written, it's false. If I had written something like C equals 40 cosine brackets 100 pi t plus pi over 2, then it would be true. Or as it turns out, even if I'd written sine, it'd be true. But how do you know? You whatever it is, whatever I give you, and what do I want you to show here? How do you show why? You take 2 derivatives with respect to time of whatever I've given you and show that it works out. Hopefully I'll do that at least once somewhere in this walkthrough, but you've got to take 2, and that means you've got to know chain rule and you've got to know your trigonometric derivatives to do it. That's it. Okay. Now we practice that more in this next part. I'm gonna change the color is annoying me. Okay. All right. Yeah, I'm just gonna let me just look at this for a second. I'm gonna turn the time. Okay, okay. I'm not gonna. Am I? Okay, I'm gonna do. I'm gonna try to go a little fast for the first one. So this is now problem 2, math. A differential equation. Okay, so this is more practice of the same, but again, as you can see, if you look at this, if you look at that equation at first, you might be intimidated. There's all of a sudden a bunch of gobbledygook in it, like a capital K, which is not, it's not the Hooke's law K, it's a different K, capital Q, a capital R. Now, the truth is all of that is coming from real physics, from electrostatic equations that we will do next. But the real point, so it's not artificial, but it is, the equation is designed to say to you, okay, can you deal with the fact that there's a bunch of new letters here that you've never seen before? And the answer is yes, you can. As long as you understand that K and Q and capital R are constants, then even though that R is cubed, which it like really is in real life in this equation, even though it's cubed, it doesn't matter. It's just a number being cubed, which makes for a new number. And then that new number is being divided by K and by Q. So it's all just one number. It's one constant. That's what we're trying to get you to get used to. And in this case, the whole equation happens to be treating a dependent variable called X. So that's not so new, right? So I'm going to say do I want to do this? Yeah, I'm going to say right now for A1, if you take what they're saying, and this is what somebody asked yesterday. I was so happy that someone, and I think it was Alexis, like admitted that she didn't love the wording, at least at first, of like show why something is or is not a solution. I'm totally with her and everybody who didn't like that wording at first, but we're getting used to it now. I think they provided you with a differential equation. I am now offering you a possible solution. What I'm asking for you to test it. I'm basically saying, here's the question. Here's a possible answer. Is it in fact a correct answer to this question? Does this cosine expression actually fit or satisfy that differential equation? And the only way to find out, I'm sure you see where I'm about to say, only way to find out is to take two derivatives. And if you're thinking, is it always two derivatives? Yes, it is. Because in this class, at this stage, it is always two derivatives because the differential equation that we're dealing with is a second order differential equation. It has a second derivative on the left side, always. If you're thinking, why, how did that even happen in the first place, or why? Why? Because F net equals MA, which is really what's really going on underneath all of this. It turns out when we say F net equals MA, what we really are saying is that in the actual physical world, the interaction, observable activity in the physical world occurs on the second derivative level. That's really what F net equals MA is saying. You don't feel velocity, right? You've been in an airplane, you've been in an elevator. You don't feel it when it's moving. You feel it when it's changing its motion, because that's a force, that's an interaction. So what we're really saying in physics is we pay attention to the second derivative level, like a lot in the physical world. So yes, we're going to take two derivatives here and see if this thing, am I really going to do them though? Okay, I'll do it once for posterity, super quickly, but I think we've done this over and over again. If I take one derivative of that x expression, if I take one derivative, right, I get, and you do want to practice this on your own, and you are expected to do this in the exam, obviously, but if I take one derivative, I'm going to get negative square root of k over r cubed x naught times cosine of all of that stuff, the square root plus pi squared over 9. I guess my big point here of the first derivative is, notice the square root term came out of the derivative due to chain rule, but the pi squared over 9 did not. Pi squared over 9 might be intimidating, but it's just a constant, so it doesn't come out of the derivative. Then if I take another derivative, the same thing happens again. So that square root thing comes out again. So a square root times the square root of a number times the square root of a number is a number. So it all comes out again. So I get this. And all of that stuff on the inside stays. Right? So I have that. I'm going to go to the next page. I'll just rewrite it. So you see the pattern. I mean, I'm sure you do. At some point, all of you, it will click in and you'll see the pattern that this thing that keeps happening, where the inner constant comes out twice because we do the chain rule twice. That's why that inner constant always gets squared on the outside, right? So put another way, that's why the inner constant has to be the square root of what's on the outside. Like this pattern, we keep doing it in one direction and we do it in the other direction. Eventually you see, and many of you already have seen, like, this is why we say that the differential equation is d2x over dt squared equals negative omega squared times x. That's just our way of saying that the omega is going to come out twice from two derivatives from chain rule. So the ultimate constant before everything we're writing is ultimately going to be the square of whatever was inside the cosine expression. So I write this, right? So this was my second derivative. And here I did two derivatives, and here's again, I guess it's worth my doing once, here again, where any among us, certainly me, even if I've done calculus and I feel like I know how to take derivatives and I do this right, if I were in the exam and it were an in-class exam and it weren't take home and I had never practiced before, I would do this and then I'd be like, now what? Right? It always makes sense when the teacher's doing it and showing you. It always, but this is where you gotta like do a rough draft or practice on your own. Or also don't save the exam for I mean, I should not have to say this, but it always happens every semester. Like, I know I'm giving you all the answers and all that. Don't get over cocky or overconfident or think I'm an over sucker and then just like leave yourself 4 hours to do the whole exam like Sunday at 10 o'clock. Because even if you think you're just going to be copying things, you're going to suddenly see things that don't make sense to you. Anyway, you get what I'm saying. Give yourself time. Anyway, here's where you would give yourself time right here at this moment. Until I had practiced this many times, I was like, okay, so what? Like, I just did all this work. Like, I don't get, like, so what? What does it mean? What it means is the thing that I think Alexis and I think Evelyn and I think Christopher and like many other people pointed out the other day. The thing is to recognize that this right here, I believe, yeah, this right here is the X that we're testing. Like the whole conjecture, the whole question was, if X equals that, does it work as a solution to the differential equation? And so there is the X. So that means when I take two derivatives of that X, apparently it does mean that I get this, oops, sorry. Times X, right? Like that. And so therefore, and if I look back at the sheet that you can't see right now, but is on my screen, if I look back, that was the differential equation that I was trying to solve. So yes, but the key, you got to recognize when you finally have written something where the X or the whatever function is embedded in it, that's the key moment to realize. Okay, anyway, so the answer to that is yes. Okay, again, this is a demonstration now, the thing I really need to get to sometime in my life. This is a demonstration that things have gotten, we actually are moving forward in the material, that pi squared over 9 that may look out of nowhere. I mean, it's an extra term and it's got a pi in it and the pi is squared, like it's intimidating perhaps. But what we just saw when we took two derivatives carefully is it doesn't throw off our game. It still allows that expression to describe harmonic oscillation. Okay, so the answer to that one is yes. Now, for the next one, I'm gonna. I'm gonna say a quick thing about this. I'm not gonna walk through it. I'm concerned about your time. I'm concerned about my time. I'm gonna tell you right now. Here's this thing that suddenly has I in it. Okay, I want you to think about this. Here's and I want you to talk about it with one another and all that. I'll start you off. But the key point is even with I, which is like, wait, where's I coming from? I is a constant. That's the first important thing to know. It's a number. It's an interesting number, just like pi is an interesting number and E is an interesting number, but it's a number. And so therefore it's treated as a constant number. Now, what number is it? Well, it says right in the sheet, by definition, I is the square root of 1. What does that have to do with anything? Why is that coming into play? Well, it's coming into play because I has an interesting impact on negative signs. And one key thing to notice about all this that I should have emphasized a million times is that the differential equation that we are talking about here has a negative sign in it. For something to be a simple harmonic oscillator, it must be described by that differential equation that most definitively, non-accidentally has a negative sign in it. Where did that negative sign come from? Originally, Hooke's law. Our differential equation is just a generalized way of writing F equals negative kx. The force is, and therefore the acceleration is always attempting to restore us to some kind of equilibrium. And there always is some kind of equilibrium in a harmonic oscillator. The force or the acceleration is always in the opposite direction from, it's always directed oppositely to our displacement from equilibrium. I mean, if we're on the right of equilibrium, the force is pulling us to the left, and vice versa. That's if the negative sign is not there, we still have a differential equation and we still have solutions, but it's a totally different differential equation and it's totally different solutions. This is very important, actually. So for any of this to work, so when we start asking, well, I guess to skip down to the bottom of the page, when we add, you can't, at the bottom of the page it says, show why the following expression is or is not a harmonic oscillator. That's English for show whether the expression upon two differentiations, whether the expression yields the differential equation that we're talking about. And it absolutely matters whether the negative, it absolutely matters whether the negative sign is there or not. Okay, so why am I saying all of this? This is where I comes in and helps us. What I want you to know, I guess I'm going to do this. Good heavens to Betsy. I is the square root of -1. Like, that's what you need to know about I. I mean, if you've never thought about it before, that's what I is. It is the name for the square root of -1. But and there's no other rules that you have to memorize or no other logic that you have to learn for the first time. You just apply all the logic of math that you already have, i.e., if that's true, then I squared most assuredly is the square root of -1 times the square root of -1, which is to say it's -1, right? And by definition, I squared is -1. You've probably seen this before. The I cubed would be I squared times I, right? Well, times I to the 1, if you like. So that means I cubed would be -1 times I, which is to say -I. I to the 4th would be I squared times I squared, which is to say -1 times -1, which is to say 1, right? Now, how far am I going to go with this, you might ask? Good question. I'm going to go one more step, and that's it. And here's why, if you haven't already. Because I to the 5th would be I to the 4th times I to the 1st, right? Which is to say 1 times I, which is to say I. Now, here's what I'm saying. Look at that. That's interesting. I cycles in steps of 4, just like cosine and sine, right? The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. The derivative of sine is cosine. 5 steps and you're back to the original. 5 steps here, you're back to the original. Interesting. I'm just pointing that out. I'm pointing out why I is even coming into our life at all, but I also have to point out one other thing. In order to answer the question in number 2, the question for the math methods, you're suddenly given this function that looks like really complicated, and it's all of a sudden, it's not a cosine, it's not a sine, but it's an e function. Why am I suddenly introducing e functions? Why am I suddenly introducing i's? Because we're looking for functions for which the second derivative with respect to time returns the original function multiplied by a constant multiplied by -1. So it's suddenly occurring to me in the middle of the math methods homework and in the middle of this exam here, it's suddenly we think, wait a second, where is cosine really the only function that does this? Just like Evelyn asked on the first day, and she, couldn't sine work? Yeah, sine could work. And are there any others? Well, what about e? One thing I want you to remember from calculus, I don't remember or deploy here, is if you're writing down GDPs for this question, one very important GDP would be if y in general, if y equals e to the x, then definitely dy dx equals, as you know, e to the x itself, right? What is e to the x? It is the function which by definition is its own derivative. Arguably, that's not just some weird, you might think, well, okay, I guess e does that, but I've never really understood what e is. That's a fascinating discussion, but in a way, what I want to say is what e is that. E is the thing that does that. Something had to do that. It's called e. E to the x is the function which changes at a rate that is identical to itself. Or e to the x is the function which is its own derivative. Does the chain rule apply to e to the x? Sure, the chain rule applies to any function. So I guess it's too late for me to cut to the chase. But so how do you solve this problem? You solve it the same way you solve the cosine or the sine. You take 2 derivatives. How do you take 2 derivatives? You realize that e to the x, the derivative of it is e to the x, and chain rule applies. So for example, just to remind you, if you have something like y equals e to the 5x, right? What would the derivative of that be? Well, because of chain rule and because of the e rule, dy dx of that would be 5 times e to the 5x. Do you see what I'm saying? Think about it if you don't. But that's the only two rules you need to apply to solve this problem here, or in the math methods. You need to know that the derivative of e to the x is e to the x, and you need to apply chain rule. And I will tell you right now, and you need to watch whether your final derivative has the negative sign in the appropriate place or not. That's really what this question is getting at. If I change the question, it might be so that it changes the situation with the negative sign. So remember, in other words, when you do the chain rule and you bring down the I, if you bring down the I 2 times because you're taking 2 derivatives, then you'll have I squared in your final answer. Don't leave it that way. Realize that I squared is -1. And then ask yourself, okay, did this work or not? I think as written, you'll find that it does work. But I think you'll also find that if I weren't there, it wouldn't work. And that's the point of I'm going to say that actually one more time to give this whole thing away. Because there's 2 things going on here. There's the exponential and there's the I. What I'm telling you right now, I don't know what the question will look like on your exam. But I guess I will tell you right now, if you practice like in homework 2, and you take 2 derivatives of that expression, pretending there was no I in there, if there was no I in there and you took 2 derivatives, you would find that your final expression does look like a constant times your original expression, but you wouldn't have a negative sign in it. That would be the problem. So if there's no I in this thing, it doesn't work. And so I don't know how I'm going to ask it on your exam, but exponential functions look like they would work. But they don't. They don't describe oscillators because they don't ultimately yield a restoring force. They don't ultimately yield that negative sign. But strangely, when you throw I into the proper place, the I takes care of things and makes it so that there is a negative sign in the final answer, and it does work. That's my summary of what's going on here. And that's a very, very interesting property. In other words, if you combine an exponential with an imaginary properly, you get a cosine. That's really what that's saying. And that's a whole fascinating branch of mathematics. But anyway, it's true. Okay. So I'm all over the place here. But basically, if you're looking at your sheets while I'm talking, you'll realize that in English, in the air, I just answered. I'm basically saying the answer to 2 is this. It is a solution. But if you took the I out, so this is the answer to Roman numeral 3 now, if you took the I out, it would not be an answer. It would not be a solution. And the reason is the negative sign will go away. Okay. And the special property of I that's making it useful for this specific problem is that it cycles through negative signs in groups of 4. Okay. The very last question of this part, I want to make checks. The very last question, part B of problem 2, I'll just say right now, if you take 2 derivatives of that thing, you are not going to get back that thing. You're going to get back, if you take 2 derivatives of that, you're going to get K, like capital K plus 0. And what I'm looking at, I'm flipping back. I'm going to change my screens again. Sorry. And obviously, everything I'm writing down right now, of course, I will post when we're done. Okay. So I'm looking at that thing now. I'm at, I believe I've pretty much answered, even though somewhat on paper and somewhat in my words. I believe I've answered all of this here, one way or another. Now, for this last bit on this page, that thing is definitely not a harmonic oscillator. If you differentiate it twice, you do not get back that thing. You get back the letter K. Now you should do that and you should show, but and honestly, if you're listening to me right now, even if the exponent were changed to a 4 or a 5 or to any finite number, if that exponent were any finite number, you're not getting back to the original. The algebraic expressions do not solve differential equations. A simple harmonic oscillator cannot be described with a power expression like this. It can only be described by functions that are infinitely differentiable, like cosine, sine, e to the x, etc. Okay. Now, what I really need to do is get to question 4, but here's question 3. Right. All right. First of all, there is definitely a video on this in last semester's playlist, and also probably the playlist from the semester before. I definitely do a full walkthrough of this. You could definitely look it up. This relates back to your lab too. The key point here, because I don't want to get bogged down, the key point here is, yeah, we're talking about something that's going back and forth now. Back and forth in an arc, at the end of a string. So now this thing is actually curved. So now there actually are actual angles involved. But the key thing is to understand that a pendulum is a harmonic oscillator, just like a mass on a spring is, as long as we make certain assumptions. And so if you treat theta as the dependent variable, all the same things can be said about theta as a dependent variable that were ever said about x as a dependent variable in a mass on a spring. This theta is now the dependent variable. It's measured in radians. Those are not the same radians as we mean when we say a half of a cycle or a quarter of a cycle or a full cycle. That can be a little bit confusing. You have to be careful about that. But this is, again, it's meant to say, even when there's actual radians in physical space involved, still, this is just another revisitation of homework 3 or of problem 1, where, in short, what we're saying is we've got a harmonic, I guess, well, can I even write? What we're saying here is we got a harmonic oscillator for which, please write this down. I can't write this down because I'm on 2 screens at once. Theta equals theta naught times cosine of omega t. What's theta naught? Well, it's given here as pi over 10 radians, right? It's literally telling you that the place where the particle has no instantaneous speed, the turning point, the place where it comes to rest, slows all the way down and then starts speeding up again. The end point, the amplitude point, that point is pi over 10 radians. So that's your theta naught. It's given, right? And omega, the angular frequency of this, that is the rate at which this thing is completing cycle 6. That's what we always mean by angular frequency, right? That is the square root of the constant in the differential equation. So it's pi over 6, that radians per second, right? So once you get that, you have a huge insight into the problem, just like you did in the other very similar ones. So you can lay that out first before you do anything, and that way you absolutely. Okay, I'm gonna switch screens again. I'm looking at the time. I'm going to switch screens again. Again, I highly encourage for this one, because I highly encourage you to look at the old videos from last semester. But let me switch screens. Well, okay, yeah. Okay, and again, I'm sort of going at the free body diagrams. All right, you might be wondering where free body diagrams suddenly come from. Wasn't that physics 203? Well, yes, it was. They never go away. We need them for the rest of physics. I will tell you right now, and again, I walk through this in much more detail in other videos, but the pure free body diagram, the pure free body diagram, which is what it's asking for here in this question, for this bob on this string. And actually, I think you thought about this a lot in the lab, but okay, here's where we would first need, this is where a diagram is really important. I'm looking back at the thing. Yeah, you notice the problem didn't provide you with a diagram, but you have to. In step 1 DFP, you have to provide a diagram. And one of the many reasons you have to, for a situation like this now goes back to what a number of people asked me from last semester. Oh, I wish I could remember who it was. But the people that, it might have been, well, people that pointed out like, oh, that Professor Walters was like really strict on coordinate systems, bless her heart. Yeah, here's an example where the reason you provide a diagram before you even do anything here is to show me which way your pendulum is being oriented so that your free body diagram can make proper sense and can be readable by me. In other words, you first, in step one, you have to draw a diagram of this pendulum because you have to make a choice at your arbitrary moment where this pendulum happens to be dangled at some angle theta from the vertical. Like, I don't know whether in your mind the pendulum is to the right or to the left of the vertical. And it doesn't matter. It's up to you, but I need to know what you're picturing. So here's like your diagram. Right. Here's your diagram. The reason you had to do that right away in step one is now when it gets, so that's a diagram. I mean, that's just a picture of the situation. It's a diagram and fact pattern, right? That's just all of the things that were given in the problem. But now you're set up because now when in part one, where it asks for a free body diagram, now the free body diagram, well, here, I'm going to go to the next page. The free body diagram will just be mg pointing down as always, and then any and all of the forces actually touching, making physical contact with the mass, and they all have to be depicted in the direction that they're actually going. So given my original diagram that at this moment the string is going like that, I stay consistent with that diagram and I say, okay, the tension in the string is pulling up on the mass like that. And in fact, let me make one other thing clearer. There's no reason to assume that tension and gravity are equal in magnitude. They're not. So I have a diagram that looks like this. Now, your FBD could be the other way. Your tension could be going the other way, but only if in your original picture, your string is going the other way. And that really makes a difference. I need to know that you know that the tension is going tangentially to the string. So part of the purpose of your original DFP is to orient me so I see what the situation is, and now I can assess this free body diagram. So this is the pure free body diagram. So it asks for that. Then it asks for you to get angular frequency. You can do that. The angular frequency is the square root of that constant. So it's pi over 6, but then it's asking 3 significant digits. That's a way of telling you, I want a number for this one. I want a number, like we're acting like this is a lab thing with measurements that you could see on a stopwatch or whatever. So if it's asking for 3 significant digits, don't say pi over 6, say, 0.577 or whatever, right? And then it says how many seconds should we expect this pendulum to take? So that's period. Yeah. Oh no. Oh, sorry. It says approximating to 3 significant digits. How many seconds should we expect this pendulum to take in order to get from one turning point to the other? Okay. So we read carefully. It's not a trick. It means what it's saying, but it is saying something specific. It's saying from one turning point to the other. One turning point to the other. So it's not saying there and back. It's not saying closed path. It's saying from one turning point to the other. So it's asking for a half cycle. It's asking you to solve for half of the period. In other words, solve for the period and divide by 2, right? And be clear about that. That's what it's asking. Okay. Then it's asking 2 things that are hard. That again, actually 3. Well, it's asking 3 things. I'm trying very hard to stay on schedule here. So I'm, feeling a little bit conflicted. I will say, in order to get the speed at t equals capital T over 4, in other words, the speed at equilibrium at a quarter of a cycle, it's asking for the speed. There are 2 distinct ways you can get this. and it alludes to that in part 6. There's 2 different ways to get this. Ultimately, it asks you to do both. I will, again, you should look at past videos on this, but the first thing is to go back to the energy conservation from homework 1. The total amount of mechanical energy at any one point has to equal the total mechanical energy at any other point. Total mechanical energy is kinetic plus potential. The potential here is not the potential due to a spring, it's the potential due to gravity. That's mgh. I'm going to say right now, you know what I'm going to say right now about these, because I'm concerned about time. These are just hard enough, but there's just enough information so you do energy conservation is one way to get the speed at equilibrium. It's asking for the speed at equilibrium. At equilibrium, there's no potential energy. That's the maximum speed. So it's just like asking for the speed at equilibrium for a spring. The 2 catches here are, one, you have to know that it's gravitational potential energy, which is mgh, not 1/2 kx squared. How do you know that? You take the integral of you do the work that gravity would do to bring something down a height h, right back to equilibrium. You integrate mg dx, but mg is a constant that comes out of the integral, whatever. Like you would show that gravitational potential energy is mgh. Then, just to help you out, h, what does h mean? It means literally height. It means the vertical displacement this thing drops. So you have to be careful and draw a diagram and show, like h is not a given in the problem. H is not the same thing as L. You have to show from a little bit of geometry or trigonometry, you have to show how you can get h in relation to the length of the string and the original angle. I mean, I'll tell you right now, what h is equal to is L minus L cosine theta. You can, if you think that through, you'll see why. Or if you look at past videos, blah, blah, blah. But I am telling you as a hint, you do have to show me that. You have to show me that gravitational potential energy is mgh. H is L minus L cosine theta. Technically, this is old physics, but we need it here. And you'll see why in a minute. And that's how you would solve for the speed at equilibrium. The other way to solve for the speed at equilibrium, that for some of you might be easier, maybe, is you know that this is a harmonic oscillator. So theta equals theta dot times cosine of omega t. That's theta. We know the definition of theta is arc length divided by radius. That's the definition of theta, right? So at any moment, again, all this actually was in lab 2. I keep acting like you've never seen this before, but you totally have. X, how far the thing travels at any moment, through actual space, is theta times r. You have the function theta equals theta naught cosine omega t, right? So if you multiply that whole thing by r, you have an expression for x. Why do I care? Like, why do I want an expression for x? Because v equals the derivative of x with respect to t. If you take the derivative of that, you'll have an expression for v, and you can just plug in all the values that are given, and you'll get an expression for v. So there's energy conservation, and there's taking the derivative of theta with respect to time. Both, you'll know you're doing it right if both those get you the same answer. And in fact, it asks you that later in the problem. So I'm not going to walk through all the details, but I'm also going to tell you, since I'm not walking through the details, I won't change that part of the question. That is the question. Just think about it in advance and practice it. But then finally, one last thing I really do have to say about this, and you really will have to think about this if you didn't heavily already in the lab. The reason it's getting into what seems like old physics, the reason it's getting into old mechanics and stuff like that is really, after it asks you to analyze this pendulum in the manner of a harmonic oscillator, at the end, the real punchline is that it's asking you to show why we believe this is a harmonic oscillator in the first place. Like, how did we come to believe that differential equation does apply to the thetas in a pendulum? And that's what you're being asked to show. Now, again, I believe you were asked to show that in lab 2. I actually don't think this is totally unfamiliar. But the way to show it is you've got to use, first of all, you've got to break up your original free body diagram. You've got to break it up into components that lie along the appropriate axes for something that's traveling in a curve. Like if this was your original, if this was your original free body diagram, like we've got to break up, those forces are neither parallel nor perpendicular with each other. We've got to break them into components. X, Y, and Z components? Well, no, because this thing's traveling in a curve. We want to break them into components that are appropriate for something traveling in a curve. We want to break them into centripetal and tangential components, or in other words, radial and tangential components. In other words, and you may want to take a sentence or two to explain that once you feel you understand it. In other words, tension is pointing purely along the radial line. It's pointing purely centripetally. It is along one of the axes of, if we're thinking of this in a circle, in polar coordinate forms, if you like, the radius is one of our axes. The vertical axis of gravity is not one of our axes. The appropriate axes to choose are like, this is an axis, and this is an axis. It's not X and Y for a circle or for a curve. It's centripetal axis and tangential axis. So it's gravity that has to be broken up. What we have if we break up gravity is something like this. It's like an inclined plane. It's like the same thing that happens with an inclined plane. Because in an inclined plane, something accelerates along a slant. It doesn't accelerate along an x-axis or a y-axis. Same thing here. The object doesn't accelerate down, or fully down. It accelerates in towards the center of the circle. We always try to line up our principal axis with the expected direction of acceleration. So this is the component free body diagram that we have, okay? And this is a pro tip for anybody who's still listening to me. Many people at this point will write in the exam that T balances with mg cos theta. They'll say T equals mg cos theta, so there's no acceleration along that axis, so we don't have to worry about it. If you'll get major points, if you're still listening to me right now, if you go out of your way to absolutely show that you know that that is wrong, it is not the case that T balances with mg cosine theta. If T were to be equal and opposite, even though my drawing totally makes it look like they do, sorry. It is not the case that those two forces are equal and opposite. If they were, there would be no acceleration along the radial line. There'd be no acceleration along the centripetal line. Then this thing wouldn't change direction. It wouldn't be in a curve. In order to curve, you have to be accelerated in toward the center of a circle. Right? This is from Physics 203. It doesn't mean you're changing your speed in that direction. It means you're changing your direction toward the center of the circle, right? Remember, acceleration is changing velocity per time. That could either mean speed or direction. So there must be acceleration along the radial line for this thing to be staying in a circle. The tension must be bigger than mg cosine theta. T minus mg cosine theta. If you here's pro tip again. I'm not even going to write it, but if you're really following me, you'll write something. I will write it. You'll write something like, in the centripetal axis, we have T minus mg cosine theta equals ma along that axis, and A along the centripetal axis for a circle always equals V squared over R, right? Otherwise, you don't have a circle. So that's true along, there's no zero along the centripetal axis. However, that's not the direction of motion. That's the direction of acceleration, but it's not the direction of motion. So when we're analyzing harmonic oscillation, we just don't care about that axis. If you followed what I just said, or if you rewind this a couple times and you make a big point in the exam, I'll really know that you're really with me. Those two forces don't balance out. They don't balance out. They yield the centripetal acceleration. However, it's the tangential acceleration that we care about, the direction, the acceleration in the direction of motion. What this diagram tells me, and then I'm really going to stop, what this, in the tangential axis, we have mg sine theta equaling ma tangential, right? And the m's cancel. And then what you do, I'm going to say this very quickly, you you say in small angle when theta is really small, as is being assumed all through here, when theta is really in the limit, when I can't believe I'm sorry, in the limit, when theta is really small, when it approaches zero, the sine of theta approaches theta itself. We argued this yesterday, like, oh, okay, and we're gonna have to end this video momentarily. I'm gonna think about what to do about it. Okay, yeah, one second. Okay, so I'm gonna end momentarily. Okay, I have to think about what to do about question 4. At the beginning of a sine function, it looks just like at the beginning of y equals sine of x, the function looks just like y equals x. I'm losing my mind. So the smaller and smaller an angle gets, the closer it gets. The smaller and smaller an angle gets, the closer the sine gets to that angle. And you could test it in radians if we're in radians. So if you type it to your calculator, if you're in radian mode and you type it to your calculator, 0.003 and then hit sine, you're going to get back something pretty close to 0.003. It won't be exactly 0.03, but it'll be pretty close. But here's the bigger important point. If you then typed in 0.00003 and hit sine, you're going to get something back that's even closer to that than the thing was before. The closer you get to zero, the closer the sine gets to the original angle. So in these small angles, we can substitute and we can say if negative g sine theta equals a, then negative g theta approximately equals a. What am I forgetting? Right. And what is a? It's that. And what is that? I'm going fast here. Okay. This is the thing we just did on the other page, that x equals r times theta by definition of theta. And what is r in this case? What's the radius of the circle? It's the length of the string. So we have this. So going to the next page, this is all approximate, but it's the smaller the angle is, the more this is true. So on the last page, what we have is this. And that is our differential equation for simple harmonic oscillation. And what that shows is that omega squared equals G over L. In other words, G over L for a pendulum is just like K over M for a mass on a spring. Just like a mass on a spring, the rate at which this thing goes back and forth is fully determined by the parameters that you could measure before you even set the thing up. It's not at all dependent on where it starts. It's dependent on how you set it up, what ingredients you use to set it up. And yes, it's approximate. If the angle is too big, then this won't work. But that's also true of a mass on a spring. If you ask it to displace too much compared to the length of the spring itself, then that won't work either. We just didn't say that explicitly when we started our life in this semester. But all things get more and more true as the conditions get more and more optimal. So the purpose of all that was to show that this really is a harmonic oscillator. And now that we've done that, you can go back and solve for G according to what you just found here. Now, that is all of the exam done in sort of more detail than I meant to, other than the last question. Right now, I'm going to say, you're still responsible for the last question because there absolutely is at least one video for the last question online that I will select and post for you. If I have time, I will make another one, explicitly for you on the last question, or I'll make some adjustment. I'm aware that I have not talked about the last question yet, but the last question anyway. But There is at least a video from last semester that I'll direct your attention to. And this is a very detailed expansion of all the other questions. So at the state right now, if we took the exam right now, I would be very aware that question 4 would be the most challenging for everybody. And I would grade it accordingly. Like in some ways, I would know, okay, they got direct answers from me from some of these things, but let's see. But if I want to really see how a person does when they're really on their own, or they're really trying to figure out things on their own, I'll see that in question 4. In other words, I'll both be more generous with question 4, but also it'll be an opportunity for people that really want to make their work shine. They might really use question 4 for that purpose. But I will try to send you more insights and support on question 4 when I can. Okay, so that's the video. We will talk. Quark plus America. And best success to everybody.